Okay, so if we're going to construct a graph of y equals 2 f of x minus 2 plus 3 for this graph, we start with a vertical stretch by factor 2. Because whatever the f function gives us is going to be multiplied by 2. What the f function gives us is what we have here. And I'm not going to go through a whole lot of explanation on this. You should recognize it. But this is something that people have not been doing well with, the vertical stretch. Draw an arrow from the x-axis up to a series of points, and then you draw an equal arrow on top of that, and you've doubled the value of the function, which is what has to happen here. So to do this, we've got to draw an arrow of the same length up here. And people pretty much insist on drawing arrows of all the same length in order to do a vertical stretch. Okay? There's half your credit gone. Okay? So this arrow has to be this long. And then an arrow here has to be this long. Arrow here has to be this long. An arrow here, this long. An arrow here, this long. So here is a graph of y equals 2f of x. Replacing x by x minus 2 means x has to be 2 units bigger to give you the same number. And that shifts the graph 2 units to the right. So 2 units is about this far. So every point on this graph is going to have to move about this far. Giving us a graph through these points. It looks pretty much like this graph, just moved to the right. And then we do the vertical shift, adding 3 units to each one. Well, 3 units would be about this much. We probably have just about enough room to do that. And I've got to do that in purple graph. Let's do it in the wrong graph. So we go up here. Go up here. And we go up here. And from this point we go up. From this point we go up. And all these blue arrows are the same length. They're all intended to be 3 units long. I'm not sure I actually drew them all the same length, but they're close enough. And if you drew them that closely, I would pretty much be okay with it. Okay? So now you have a graph where the purple graph has been raised 3 units. Got a little close to the top of the board there, so the shape looks a little weird at that point. But you get the idea. I could have done the same thing with this graph, right? What would happen to my zeros? Well, when I vertically stretch it, my zeros would stay where they are, right? Now, when I horizontally shift it, my zeros would move over 2 units, okay? But I'd still know where my zeros are. Then when I lift it up 2 units, 3 units, well, that messes up my zeros. They change, okay? They change in a predictable way with a horizontal shift, But when I do the vertical shift, you don't know where they're going to be. Okay? Now the other thing though is I could write out this function. I could write out 2f of x minus 2 plus 3. I just replace every x by an x minus 2, then add 3 on the end, and put a 2 out in front of it. So our polynomial, let's give this a name, p of x. We'll just make a note here that okay, 2p of x minus 2 plus 3. Now there's the same expression here, but for the polynomial, p of x. What's that going to be? It's going to be 2. I don't know if I'll get all this in here. Multiplied by x minus 2 minus 4 times x minus 2 squared plus 6 times x minus 2 plus 2 multiplied by x minus 2 squared plus x minus 2 plus 6 and then I got to be careful, I need an extra set of parentheses out here. Okay, then it's going to be multiplied by x minus 2 plus 2 squared multiplied by x minus 2 minus 3 squared. So 2 times all of this. So let's put the 2 out here where we can really see it. And then plus 3. Just using function notation, all this says is replace every x by x minus 2, which I've done. Okay? Then put a 2 out in front of it. You've got to put parentheses around it all. Multiply it all by 2, and then you add the 3. Now, you could simplify this, right? Okay? X minus 2 minus 4 is what? Minus 2 minus 4 is minus 6. That becomes x minus 6, right? Now, you got to do a little more work here. You got to expand x minus 2 and do all the stuff in here, but these are easy to simplify. You can simplify all of these. Okay? The reducible quadratic could conceivably become irreducible. I don't think it would, but it might. Okay? Or a reducible quadratic, an irreducible quadratic could become reducible because you're changing all the coefficients of x squared and x and the number left over. Okay? So the b squared minus 4ac thing might work out one way, might work out another. Anyhow, so you see that we could, given the graph, we could see what happens to the graph by the vertical stretch, the horizontal shift, and the vertical shift. It's going to stretch out, it's going to move over a little bit, it's going to move up a little bit. And we can also see what happens to the equation of the function. So I could ask you to do that. Okay? I probably wouldn't make the polynomial this long on the test. I might give you a couple of linear factors and a quadratic factor and ask you to figure out whether the quadratic is reducible. And I might ask you to shift it, and I'd ask you to do that for homework. Okay? Transform it.
Yeah, we got this.
And then see if you can make sense out of what you did. Not just being able to graph the thing is probably half your credit on a problem like that, right? Then being able to do the shifts is probably another 3 points, or maybe it's 4 and 4
If they weren't, then it's not because.
out of 10 points. And then being able to make sense out of it, your last 2 points. Okay? That make sense? So, you want to think about it.